Okay, so we're talking about chemical equations and chemical reactions, and we had talked a little bit about the first 2 points here that, we had talked about this, and we had talked about the fact that a chemical equation has to represent known facts and has to have the correct formulas for the reactants and products. And so the last thing we were going to talk about under this was that the law of conservation of mass has to be satisfied. So in order to talk about satisfying law of conservation of mass, we kind of have to remember what it is. Basically, it says you can't create or destroy matter. So you cannot create an atom from nowhere, and you can't destroy an atom in the course of an ordinary chemical reaction. That takes fission or fusion, which means that we have to have the same number of atoms of all elements on both sides. They can change dance partners, but they have to stay. And we use coefficients to equalize those numbers of atoms. If you change subscripts, you are changing a chemical formula. If you change a chemical formula, then the equation no longer represents known facts. You're making stuff up as you go. When we do chemical formula writing, we typically start with what's called a word equation. We start with a sentence that describes a reaction. And from that, we tend to write a word equation. So, if we have this sentence, okay, so we usually start off with a sentence that describes a reaction. And so the sample sentence I've given you here is that methane gas reacts with oxygen gas to form water and carbon dioxide. How do we know it's a sentence? It's all words. It has a capital letter at the front and has a period at the back, sort of basic English grammatical stuff. There are no symbols in this sentence. There are no chemical formulas in this sentence. This is a sentence. And, I can identify usually subject and, I'm not even sure I can go beyond that. I can identify subject and verb. So I guess the subject here would be methane gas. There's a verb, it's doing something. There's an object, all that good stuff that makes it a sentence. When we go from a sentence that describes a reaction and we're working towards making an actual equation, we start off by writing what's called a word equation. Do not confuse word equations and sentences. They are different. Let me move this out of the way. So a word equation takes just the words from this sentence that are chemicals and puts them in the sentence. So we would keep methane. Instead of saying methane gas, we would put a little G down there. Plus oxygen, also with a little G. An arrow is, an arrow is what shows where you divide the products and the reactants. So methane gas plus oxygen gas react to form water and carbon dioxide. Now, we weren't given any state information about the water and the carbon dioxide, so we can't specify. We can't make stuff up. Later you'll figure out some clues for discerning what in fact they are. This is a word equation. Okay. Notice that it's not a sentence. It's different than a sentence. If I give you a sentence and ask for a word equation, don't give me a sentence back. It is not the same thing. So a word equation replaces words that indicate parts of the reaction with symbols. So any place you've got something like gas, that gets replaced with a little symbol indicating state. Those pluses stand in for with, and also becomes a plus sign. The one part that people tend to have a problem with is thinking that you can directly translate, I just plug these in order. You don't. Here, the word reacts comes before oxygen gas. But you have to read that sentence and understand that methane is reacting with oxygen gas to know that The arrow that indicates a reaction has occurred comes after the oxygen gas. The methane and the oxygen gas are the two reactants. The two products are out here. So that's your first step, writing a word equation. When you have your test for this chapter, I'll give you a sentence and I will ask you to write me a word equation, a formula equation, and a balanced chemical equation. You need to be able to do all three of those and understand what the difference is. So then, once we have this, okay, once we've got that word equation written, then we go in and for every word that references a chemical compound or element, a chemical basically, we're going to substitute a formula. So that means you have to be able to write correct formulas. So methane, that's an organic compound. You don't necessarily know that. It's CH4. What form does oxygen gas exist in? O2, because it's diatomic, always. So this is going to be O2. Oh, I don't want to forget my little state symbols here. Water. H2O. Now, we weren't told what form this was in, so we can't put in a state symbol. And then carbon dioxide, that's rules for molecular naming. That's CO2. And we weren't given state information on either of those. This is a formula equation. What do you notice about it? So if we think back to the things that chemical equations have to do, they have to represent known facts, they have to represent actual reactions, have to represent correct formulas, have to satisfy the law of conservation of mass. Does this satisfy the law of conservation of mass? What do you think? It doesn't, yeah, it's not balanced. So formula, that's okay actually, because a formula equation is not balanced. A formula equation is just a chemical equation that hasn't been balanced yet. Once it's been balanced, we call it a chemical equation. So, formula equation is not balanced. To balance it, you have to make sure that you have the same number of atoms on each side. I have, it's not really patented, but I say it's my patented method. I made it up myself. And it works really well. As you get better at these, just like with writing formulas, once you're really proficient at this, you probably won't write down everything, but starting off, I would strongly advise that you do. So these next two slides are all about balancing. I'm going to skip them in favor of just kind of doing this my longhand way. So we'll go ahead, and when I balance a chemical equation, I write, oops, CH4, Moser. Okay, this is how I start off balancing a chemical equation. I draw a line down from the arrow showing reactants and products, and I list how many of each atom I'm starting off with. So I'm starting off with 1 carbon, 4 hydrogens, 2 oxygens on the reactant side, 1 carbon, 2 hydrogen, and how many oxygens on the product side? Yes, be careful. It's a trap because you want to look at either this one or this one, but you have to look at them both. So there are 3 oxygens. So I have to get those numbers to match. Now, I leave myself a little bit of space in front of these. And what I tend to do is I'll pop a number in. I don't erase those tallies that I've got. I just put a line through them and then put in the new total, because that way you've got sort of a breadcrumb trail to trace back if you screw something up. This one's pretty easy, but they do get more complicated. The thing that you want to balance last is anything that's all by itself, because those are easy. Now, that means oxygen is going to be the last thing we're going to balance. We're not going to change the coefficient on the O2 until the very end, because we can make the O2 be whatever we want, with one caveat. It has to be a multiple of 2. So we have to end up with an even number of oxygens on this side. Okay, so if we start off, we know that we have to at least double the hydrogen. So I'm going to put a 2 there. That now brings me up to 4 hydrogens, 4 oxygens, 1 carbon. Is there any fast, easy way to make... So right now, carbon's balanced, hydrogen's balanced. Oxygen's the easy one. Is there anything I could do to get my total number of oxygen atoms on the reactant side to be 4? Put a coefficient 2 here. I'm done. That's it. So when you would rewrite this, you would get rid of those blanks, and you would just say CH4 plus 2O2 yields 2H2O plus CO2. Okay? Do you want to do one more together, or do you want to just be cut loose to work on practice? You can do one more. Okay, so to read, now I'm starting you off with balancing practice where you don't have to go from a sentence to a word equation to a formula equation to a balanced equation. Just getting the balancing practice in. Then I'll hand you the next practice sheet, which has you going from sentences, writing formulas, doing all of it. But I want to start you off slow. So here we have ammonium phosphate reacting with lead-4 nitrate to form lead-4 phosphate and ammonium nitrate. Here's the question that everybody asks right off. Do we have to break up all those elements? It's a qualified no. If the polyatomic ions do not break apart, if they stay in chunks on each side of the equation, if they're just changing dance partners, you can balance it using the polyatomic ions, which is much, much, much easier than if you break them all apart and try to balance oxygen and nitrogen and phosphorus. So go ahead and list, whoops, and then I just went ahead and did it anyway. So list your polyatomic ions. So we have NH4 ammonium ions, we have phosphate ions, PO4, we have lead-4 ions, and we have nitrate ions. And I'm going to list the exact same things on the other side of the equation. Okay, so how many ammonium ions do I have? On the reactant side, I should say. Fingers. 3. Yes. This subscript 3 tells me I have 3 ammonium ions. How many phosphate ions? Oh, I should do, my normal is to do this in the, so 3, 1 phosphate ion. How many lead ions? 1. And how many nitrate ions? 4. On the other side, how many ammonium ions? Vote with fingers. 1. How many phosphate ions? 4. Lead? 3. Nitrate? 1. Well, what a mess. Well, I know one thing. At a very bare minimum, I'm going to have to triple the number of lead ions over here. So let's try something. So that gives me now 3 lead, 12 nitrate. So is anything balanced right now? Well, lead's balanced. And I know that at a bare minimum, I'm going to have to quadruple the number of phosphate ions over here. So if I do 4 there, now I have 12 nitrate ion, or 12 ammonium ions, and 4 of that. Interesting. Lead and phosphate are balanced. Ammonium and nitrate, this is nice because they're not all, I mean, they're not alone, but there's just one of each in that compound, so whatever coefficient I put in front of it is going to automatically give me that number. So is there a way to get 12 ammonium and 12 nitrate? Easy peasy. 12. Okay. It is just a matter of practice. I chose this one. I can tell you what would have happened, and this, you'll do this on some of them, I promise. I call it the upward death spiral. You just keep adding. So if you started out with the nitrate and the ammonium, you might try putting a 4 there, and then you try to balance this. Go for the things that are going to be the easiest to balance at the end. And do this sort of little tally system to start at least. Okay? That's it. I'll hand you the worksheet. You can practice when you finish with that one. I'll give you the harder one.